Lightning, a dramatic display of electrical power, often raises questions about its interaction with the Earth and the effectiveness of grounding systems. Let's delve into the science behind lightning strikes and the role grounding plays in mitigating their impact. A common misconception is that lightning is solely attracted to land, given the narrative often presented of streamers from ground-based objects connecting with downward leaders from the sky. However, a significant portion, estimated to be around 85%, of lightning strikes occur over water, particularly oceans and the Gulf of Mexico. This raises the question: if lightning seeks the Earth, why does it predominantly strike non-land locations? The answer lies in understanding that lightning seeks the easiest path to ground, and in the case of water, the conductivity of seawater provides that path. The salt content in seawater acts as an excellent conductor of electricity, allowing the lightning to effectively connect to the Earth beneath the surface of the water. So, while it may not be land in the traditional sense, the water facilitates the grounding process. Shifting our focus to aviation, it is estimated that 1 in 5 aircraft flights experience a lightning strike or are affected by lightning. This scenario again highlights the apparent absence of direct Earth involvement. Why, then, does the National Electrical Code or NEC place such emphasis on connecting electrical systems to Earth as a measure of lightning protection? The NEC recommendation stems from the understanding that lightning strikes can occur anywhere, including over land and affecting aircraft. While grounding cannot guarantee complete prevention of lightning strikes, it provides a designated safe pathway for the electrical current to travel, minimizing the potential for damage to electrical systems and building structures. Grounding achieves this in several important ways. Firstly, grounding helps redirect the electrical current away from sensitive equipment that could be damaged by a surge of electricity. Secondly, grounding facilitates the dissipation of electrical energy safely into the Earth, preventing the buildup of dangerous voltages. Thirdly, grounding helps create an equipotential plane around the building structure, which reduces the risk of arcing and other hazardous electrical phenomena. Now, let's consider the statistics related to lightning damage. It is estimated that lightning causes approximately $2 billion in losses to utilities in the United States and over $1.7 billion in losses to homes annually. Insurance companies process around 300,000 claims each year due to lightning damage. Do these substantial figures suggest that the grounding of electrical systems is effective in protecting against lightning? Or, conversely, do they indicate that these incidents occur because grounding was inadequate at the affected buildings and facilities? Alternatively, do these numbers imply that effective grounding makes little difference in protecting against lightning? The truth is more nuanced than a simple yes or no answer. The high volume of lightning-related claims and financial losses suggests that grounding alone may not provide complete protection against lightning. However, these statistics do not necessarily indicate that grounding is ineffective. It is important to consider that some of the reported damages may have occurred in structures that were not properly grounded in the first place. It is also possible that grounding systems were compromised due to factors such as corrosion, improper installation, or inadequate maintenance. Furthermore, other variables, such as the intensity of the lightning strike, the presence of flammable materials, and the overall design of the building, can influence the extent of the damage. In conclusion, while grounding may not guarantee absolute protection against lightning, it remains a highly recommended practice according to the NEC and other electrical safety standards. By offering a secure and reliable route for electrical current, grounding significantly reduces the risk of damage to electrical systems, building structures, and, most importantly, human lives. It is crucial to recognize that grounding is just one component of a comprehensive lightning protection strategy. Other measures such as surge protection devices, lightning rods, and proper building design can further enhance safety and minimize the potential for lightning-related damage. Let's examine the components and function of grounding systems in greater detail, as they are implemented in electrical systems for safety and protection against lightning strikes. Grounding systems serve multiple critical roles. Firstly, they provide a low-impedance path for fault currents, facilitating the rapid operation of overcurrent protective devices such as circuit breakers and fuses, which disconnect the faulty circuit and prevent electrical shock hazards. Secondly, grounding systems limit the voltage on equipment enclosures and conductive parts, reducing the risk of electric shock. Thirdly, grounding systems help stabilize the voltage to ground during normal operation, preventing voltage fluctuations that can damage equipment. Fourthly, as we have discussed, grounding systems provide a path for lightning currents to dissipate safely into the earth, minimizing damage to electrical systems and structures. A typical grounding system consists of several key components. The grounding electrode is a conductive object buried in the earth that provides a direct connection to ground. Common grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The grounding electrode conductor connects the grounding electrode to the electrical system at the service entrance. This conductor must be sized appropriately to handle the maximum fault current that could flow to ground. The equipment grounding conductor provides a low impedance path for fault currents from equipment enclosures back to the source. This conductor is typically a wire or conduit that is run with the circuit conductors. The bonding jumpers connect metallic equipment enclosures, raceways, and other conductive parts to the grounding system. This ensures that all conductive parts are at the same potential, reducing the risk of electric shock. Effective grounding requires careful design and installation. Firstly, the grounding electrode must be installed in an area with low soil resistivity to ensure a good connection to ground. Secondly, the grounding electrode conductor must be sized appropriately to handle the maximum fault current. Thirdly, all connections must be made securely and be protected from corrosion. Fourthly, the grounding system must be inspected and tested regularly to ensure that it is functioning properly. Now, let's turn our attention to the NEC requirements for grounding and bonding. The NEC provides detailed requirements for grounding and bonding in Article 250. These requirements are designed to ensure the safety of electrical systems and to protect against electric shock and fire hazards. Some of the key NEC requirements for grounding include grounding electrode system. The NEC requires that all buildings and structures with electrical systems have a grounding electrode system. This system must consist of one or more grounding electrodes that are bonded together to form a single grounding system. Grounding electrode conductor. The grounding electrode conductor must be sized in accordance with NEC Table 250.66 based on the size of the service entrance conductors. Equipment grounding conductor. The equipment grounding conductor must be sized in accordance with NEC Table 250.122 based on the rating of the overcurrent protective device protecting the circuit. Bonding. The NEC requires that all metallic equipment enclosures, raceways, and other conductive parts be bonded together to form a continuous electrical path to ground. Ground fault circuit interrupters or GFCIs. The NEC requires that GFCIs be installed in all wet locations such as bathrooms, kitchens, and outdoor areas. GFCIs protect against electric shock by detecting ground faults and interrupting the circuit. It is important to note that the NEC is a minimum safety standard. In some cases, it may be necessary to exceed the NEC requirements to ensure adequate grounding and bonding. In addition to the NEC requirements, there are other industry standards and best practices for grounding and bonding. These standards provide more detailed guidance on the design, installation, and maintenance of grounding systems. Some of the relevant industry standards include IEEE Standard 142, Recommended Practice for Grounding of Industrial and Commercial Power Systems, and ANSI or NET-MTS, Standard for Maintenance Testing Specifications for Electrical Power Equipment and Systems. These standards provide valuable information on topics such as grounding system design, soil resistivity testing, and ground impedance measurement. Now, let's discuss some common grounding mistakes and how to avoid them. Improper grounding electrode installation. One common mistake is to install the grounding electrode in an area with high soil resistivity. This can result in a poor connection to ground and reduce the effectiveness of the grounding system. To avoid this mistake, it is important to test the soil resistivity before installing the grounding electrode and to select a location with low soil resistivity. Incorrect grounding electrode conductor sizing. Another common mistake is to use an undersized grounding electrode conductor. This can result in the conductor overheating and failing during a fault condition. To avoid this mistake, it is important to size the grounding electrode conductor in accordance with NEC Table 250.66. Loose or corroded connections. Loose or corroded connections can increase the impedance of the grounding system and reduce its effectiveness. To avoid this mistake, it is important to make all connections securely and to protect them from corrosion. Failure to bond equipment enclosures. Failure to bond equipment enclosures can create a shock hazard. To avoid this mistake, it is important to bond all metallic equipment enclosures, raceways, and other conductive parts together to form a continuous electrical path to ground. Improper use of GFCIs. Improper use of GFCIs can render them ineffective. To avoid this mistake, it is important to install GFCIs in all wet locations and to test them regularly to ensure that they are functioning properly. Proper grounding and bonding are essential for electrical safety. By following the NEC requirements and industry best practices, it is possible to design, install, and maintain effective grounding systems that protect against electric shock and fire hazards. Now let's consider the specific application of grounding and lightning protection systems. Lightning protection systems are designed to protect buildings and structures from damage caused by lightning strikes. These systems typically consist of lightning rods, down conductors, and a grounding system. The lightning rods are installed on the roof of the building and are designed to intercept lightning strikes. The down conductors are connected to the lightning rods and provide a path for the lightning current to flow to ground. The grounding system dissipates the lightning current safely into the earth. The grounding system for a lightning protection system must be designed to handle the high currents associated with lightning strikes. The NEC provides specific requirements for ground and lightning protection systems in Article 250. In addition to the NEC requirements, there are other industry standards and best practices for grounding lightning protection systems. These standards provide more detailed guidance on the design, installation, and maintenance of these systems. One of the relevant industry standards is NFPA 780, standard for the installation of lightning protection systems. This standard provides comprehensive information on all aspects of lightning protection, including grounding. Let's delve deeper into the NEC requirements for grounding and bonding systems. The NEC, or National Electrical Code, SOS, is the cornerstone for safe electrical installations. Article 250 of the NEC is entirely dedicated to grounding and bonding, providing detailed guidelines to ensure electrical safety and minimize the risk of electric shock and fire hazards. Let's explore some of the key aspects of Article 250. Grounding electrode systems. Section 250.50 of the NEC mandates that all buildings or structures supplied by an electrical system must have a grounding electrode system. This system serves as the foundation for grounding, providing a direct connection to the earth. Acceptable grounding electrodes include metal underground water pipe. This is often the primary grounding electrode, provided it meets certain requirements, such as being in direct contact with the earth for at least 10 feet. Ground ring. A bare copper conductor, no smaller than 2 American wire gauge or AWG, encircling the building and buried directly in the earth at a depth of at least 2.5 feet. Rod and pipe electrodes. These must be at least 8 feet long and driven into the earth. Rod electrodes must be at least 5/8 inch in diameter, while pipe electrodes must be at least 3/4 inch in diameter. Plate electrodes. These must have a surface area of at least 2 square feet and be buried at least 2.5 feet below the surface of the earth. Other listed electrodes. Other types of electrodes that are listed and labeled for grounding purposes are also permitted. Bonding of electrodes. If a building has multiple grounding electrodes, they must be bonded together to form a single grounding electrode system. This ensures that all electrodes are at the same potential, reducing the risk of voltage differences and ground loops. Grounding electrode conductor. The grounding electrode conductor, or GEC, connects the grounding electrode system to the electrical system. The size of the GEC is determined by NEC Table 250.66, based on the size of the service entrance conductors. The GEC must be made of copper or other corrosion-resistant material and must be securely connected to the grounding electrode and the electrical system. Equipment grounding conductor. The equipment grounding conductor, or EGC, provides a low-impedance path for fault currents from equipment enclosures back to the source. The EGC is typically a wire or conduit that is run with the circuit conductors. The size of the EGC is determined by NEC Table 250.122, based on the rating of a current protective device protecting the circuit. The EGC must be connected to all metal enclosures, raceways, and other conductive parts of the electrical system. Bonding. Bonding is the process of connecting all metal parts of an electrical system together to create a continuous electrical path to ground. Bonding reduces the risk of electric shock by ensuring that all metal parts are at the same potential. The NEC requires that all metal enclosures, raceways, and other conductive parts be bonded together using bonding jumpers. Bonding jumpers must be sized appropriately for the size of the circuit conductors and must be securely connected to the metal parts. Ground fault circuit interrupters. Ground fault circuit interrupters, or GFCIs, are life-saving devices that protect against electric shock. GFCIs work by monitoring the current flowing in a circuit and detecting any leakage current to ground. If a ground fault is detected, the GFCI will trip the circuit, interrupting the flow of electricity and preventing electric shock. The NEC requires that GFCIs be installed in all wet locations, such as bathrooms, kitchens, and outdoor areas. GFCIs are also required in certain other locations, such as construction sites and healthcare facilities. Surge protection devices. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning strikes, power line disturbances, and other events. SPD work by diverting the surge current to ground, preventing it from damaging sensitive electronic equipment. The NEC recommends the use of SPD in all electrical systems, especially in areas prone to lightning strikes or power line disturbances. SPD should be installed at the service entrance and at individual equipment locations. In addition to the NEC requirements, there are other industry standards and best practices for grounding and bonding. These standards provide more detailed guidance on the design, installation, and maintenance of grounding systems. Some of the relevant industry standards include IEEE Standard 142, Recommended Practice for Grounding of Industrial and Commercial Power Systems, and ANSI or NETA NTS Standard for Maintenance Testing Specifications for Electrical Power Equipment and Systems. These standards provide valuable information on topics such as grounding system design, soil resistivity testing, and ground impedance measurement. Effective grounding and bonding are essential for electrical safety. By following the NEC requirements and industry best practices, it is possible to design, install, and maintain effective grounding systems that protect against electric shock, fire hazards, and equipment damage. Remember, electrical work can be dangerous. Always consult with a qualified electrician when working with electrical systems. Let's expand on the crucial role of grounding in mitigating the risks associated with lightning strikes. Lightning strikes are characterized by extremely high voltage and current levels, posing a significant threat to electrical systems and building structures. Grounding plays a vital role in safely dissipating this energy into the earth, minimizing the potential for damage and injury. When lightning strikes a building, the surge of electrical energy seeks the path of least resistance to ground. Without a properly designed and installed grounding system, this energy can travel through electrical wiring, plumbing, and other conductive materials, causing extensive damage and creating a fire hazard. A well-designed grounding system provides a dedicated low-impedance path for the lightning current to flow to ground. This path typically consists of lightning rods, down conductors, and a grounding electrode system. Lightning rods are installed on the roof of the building and are designed to intercept lightning strikes. They are typically made of copper or aluminum and are positioned to provide a zone of protection for the building. Down conductors are connected to the lightning rods and provide a path for the lightning current to flow to ground. They are typically made of heavy gauge copper or aluminum wire and are installed on the exterior of the building. Grounding electrode system. The grounding electrode system dissipates the lightning current safely into the earth. It typically consists of ground rods, ground plates, or a combination of both. The grounding electrode system must be designed to handle the high currents associated with lightning strikes. The NEC provides specific requirements for grounding lightning protection systems in Article 250. These requirements cover the size and type of grounding electrodes, the size and routing of down conductors, and the bonding of metal parts. In addition to the NEC requirements, there are other industry standards and best practices for grounding lightning protection systems. One of the relevant industry standards is an FPA 780 standard for the installation of lightning protection systems. This standard provides comprehensive information on all aspects of lightning protection, including grounding. Effective grounding is essential for a lightning protection system to function properly. A poorly designed or installed grounding system can actually increase the risk of damage from a lightning strike. For example, if the grounding system has high impedance, the lightning current may find an alternative path to ground through the building's electrical wiring, causing damage to sensitive electronic equipment. To ensure effective grounding, it is important to use qualified lightning protection contractors who are familiar with the NEC requirements and industry best practices. These contractors can assess the specific needs of the building and design a grounding system that provides adequate protection against lightning strikes. In addition to grounding, other measures can be taken to protect against lightning strikes. These measures include surge protection devices. SPT can be installed at the service entrance and at individual equipment locations to protect against voltage surges caused by lightning strikes. Shielding can be used to protect sensitive electronic equipment from electromagnetic pulses or EMP generated by lightning strikes. Tree protection. Trees can be protected from lightning strikes by installing lightning protection systems on them. Proper maintenance. Regular inspection and maintenance of lightning protection systems are essential to ensure that they are functioning properly. By combining effective grounding with other lightning protection measures, it is possible to significantly reduce the risk of damage and injury from lightning strikes. The question of why lightning seems to favor striking water surfaces, especially oceans, despite its apparent need for a connection to the earth, can be clarified by understanding the physics of electrical discharge and the properties of seawater. Lightning seeks the path of least resistance to ground, and in the case of oceans, the high conductivity of seawater provides this path. Seawater contains a significant amount of dissolved salts, primarily sodium chloride, which dissociate into ions. These ions, such as sodium ions and chloride ions, are free to move and carry electrical charge. This ionic conductivity makes seawater a much better conductor of electricity in freshwater or dry land. When a charged cloud approaches the ocean surface, it induces an opposite charge in the water below. This charge buildup creates a strong electric field between the cloud and the water. As the electric field intensifies, the air becomes ionized, creating a conductive channel through which the lightning can discharge. Because seawater is a good conductor, the lightning can easily travel through the water to reach the earth below. In contrast, dry land is a relatively poor conductor of electricity. The soil contains minerals and organic matter, but these materials do not conduct electricity as efficiently as seawater. As a result, lightning is more likely to strike a tall object on land, such as a tree or building, which provides a shorter path to ground. However, when a large expanse of conductive water is available, the lightning is more likely to strike the water surface directly. Furthermore, the curvature of the earth plays a role in the distribution of lightning strikes. The oceans cover a larger surface area than land, and they are more evenly distributed around the globe. This means that there is a greater chance of a charged cloud being located over the ocean than over land. In addition, the warm, moist air over the oceans creates a favorable environment for the formation of thunderstorms, which are the source of lightning. In summary, lightning strikes tend to occur more frequently over water surfaces due to the high conductivity of seawater, the large surface area of the oceans, and the favorable conditions for thunderstorm formation. While lightning does require a connection to the earth to complete the circuit, the seawater provides an efficient pathway for the electrical discharge. When considering the effectiveness of grounding systems in protecting against lightning damage, it is important to acknowledge the limitations of grounding alone. While grounding is a crucial component of a comprehensive lightning protection strategy, it does not guarantee complete protection against all lightning strikes. The amount of damage caused by a lightning strike depends on a number of factors, including the intensity of the strike, the design of the building, and the presence of other protective measures. Grounding systems are designed to provide a low impedance path for the lightning current to flow to ground, but they cannot prevent the lightning from striking in the first place. In addition, even a well-designed grounding system may not be able to handle the full force of a very intense lightning strike. Some of the lightning current may still find its way into the building's electrical wiring, plumbing, or other conductive materials, causing damage. Furthermore, grounding systems can be compromised by factors such as corrosion, improper installation, or inadequate maintenance. If the grounding system is not properly maintained, its effectiveness may be reduced, increasing the risk of damage from a lightning strike. To provide the best possible protection against lightning damage, it is important to combine grounding with other protective measures such as surge protection devices, lightning rods, and proper building design. Surge protection devices (SPD) can be installed at the service entrance and at individual equipment locations to protect against voltage surges caused by lightning strikes. Lightning rods can be installed on the roof of the building to intercept lightning strikes and provide a direct path to ground. Proper building design: the building can be designed to minimize the risk of lightning damage by using non-conductive materials, avoiding sharp corners, and providing adequate spacing between conductive elements. Regular inspection and maintenance: regular inspection and maintenance of all lightning protection measures are essential to ensure that they are functioning properly. By combining these measures, it is possible to significantly reduce the risk of damage and injury from lightning strikes. It is also important to recognize that lightning protection is not a one-size-fits-all solution. Specific measures that are needed will depend on the location of the building, the type of building, and the value of the content. A qualified lightning protection contractor can assess the specific needs of the building and design a protection system that provides adequate protection against lightning strikes. When discussing grounding systems, it is essential to differentiate between system grounding and equipment grounding, as they serve distinct but equally important roles in electrical safety. System grounding involves connecting the neutral point of an electrical power system to the earth. This connection provides a stable voltage reference and helps to limit the voltage to ground during normal operation. System grounding also facilitates the operation of overcurrent protective devices, such as circuit breakers and fuses, during ground faults. In contrast, equipment grounding involves connecting the metal enclosures of electrical equipment to the earth. This connection provides a low impedance path for fault currents, helping to prevent electric shock hazards. Equipment grounding also helps to reduce electromagnetic interference, or EMI. The NEC provides specific requirements for both system grounding and equipment grounding in Article 250. These requirements cover the size and type of grounding conductors, the methods of connecting to grounding electrodes, and the bonding of metal parts. In general, system grounding is required for most alternating current or AC power systems. The type of system grounding that is used depends on the voltage and configuration of the power system. Common types of system grounding include solidly grounded systems. In this type of system, the neutral point is directly connected to the earth. This provides a very low impedance path for fault currents, but it can also result in high fault currents. Impedance grounded systems: in this type of system, an impedance, such as a resistor or reactor, is inserted between the neutral point and the earth. This limits the fault current, but it also increases the voltage to ground during a fault. Ungrounded systems: in this type of system, the neutral point is not connected to the earth. This provides the highest level of protection against fault currents, but it can also result in high voltage to ground during a fault. Equipment grounding is required for all metal enclosures of electrical equipment that are likely to become energized. This includes enclosures of motors, transformers, switchgear, and other electrical equipment. The equipment grounding conductor must be sized in accordance with NEC Table 250.122, based on the rating of the overcurrent protective device protecting the circuit. The equipment grounding conductor must be connected to the metal enclosure using a listed connector. In addition to the NEC requirements, there are other industry standards and best practices for system grounding and equipment grounding. These standards provide more detailed guidance on the design, installation, and maintenance of grounding systems. The effectiveness of a grounding system depends on a number of factors, including the soil resistivity, the size and type of grounding electrodes, and the quality of the connections. It is important to test the grounding system regularly to ensure that it is functioning properly. Grounding systems are tested using a variety of methods, including soil resistivity testing. This test measures the resistance of the soil to the flow of electrical current. The soil resistivity is an important factor in determining the effectiveness of a grounding system. Ground impedance testing. This test measures the impedance of the grounding system to the flow of electrical current. The ground impedance should be as low as possible to provide a lower impedance path for fault currents. Continuity testing. This test verifies that all metal parts of the electrical system are properly bonded together. The continuity test should show a low resistance between all bonded parts. Visual inspection. A visual inspection of the grounding system can identify any obvious problems, such as corroded connections or damaged conductors. By performing regular testing and maintenance, it is possible to ensure that a grounding system is functioning properly and providing adequate protection against electric shock and fire hazards.